Hey, what's up guys? So as promised, I'm redoing the video from this past Monday's review session. I ran out into a little bit of a problem, so I'm just doing it again. So we started talking about chapter 5 the week prior to this Monday that just passed. We met on the 2nd of October. So the session before that, we went over isomerism and RNS configurations. So we're going to go into a little bit more detail regarding that and incorporate some new concepts that you guys have not seen yet. So just to review, we were talking about stereoisomers, and we also spoke about constitutional and structural isomers. So if you guys want a good understanding of that, you can refer to the video right before this one that's already posted, and then come back to this one. Okay, so we talked about diastereomers, and we explained how they're pretty much structures that have different physical properties, but similar chemical properties. And this is going to be really important in Orgo Lab. If y'all are in it, y'all are going to pretty much be seeing that firsthand. And the second one we have are enantiomers. Now the thing about enantiomers is that they have identical physical properties and chemical properties, except when they interact with molecules with other chiral agents. So the two things that y'all want to take from here are diastereomers and enantiomers. Okay. So I have a couple figures drawn on this sheet for you guys. I'll give y'all a second to just copy them down, and then I'll go forward with what I want to do with these questions, okay? Also, whenever we're doing our review sessions in person, or if I have to resort to this because I ran out of space on the card, which is why I didn't record them. No matter how I'm doing it, I highly recommend writing down what I'm doing, because if you have them at your availability to look at while you're doing hardcore practice, it's only going to be easier. So, okay. We have these structures, the ones in these little squiggly lines on here. So what we're going to do is we're going to one by one go through these and see how they compare to each other, if they are diastereomers or enantiomers, okay? So as you can see, we have this structure here, both with wedges on the halogens here, and I'm asking how do they compare to this one. So these structures are the same on here, but their orientation is flipped. So this is showing you this structure having these structures alternated on the opposite direction. So as you can see, these would definitely be enantiomers because they have the identical physical property. It's just flipped. So if you have two structures and they're shown in another structure having the exact opposite configuration, meaning both changed, then it's an enantiomer. Okay, I'll probably use a red pen for this. Okay. Now this one, we have the two dashes going to this figure. So the bromine is on a dash going to a wedge. So one completely changed, and one is a dashed chlorine and another one's a dashed chlorine. So one changed and one didn't. So as you can remember from the prior session, I referred to diastereomers in a good way by saying one mirror, one non-mirror. So if you remember it like this, you'll never get it wrong. You'll always get it right. And this is for diastereomers. So that's exactly what we have. One changed, one's a mirror, and one's not. So we know this one is going to be diastereomer. Okay, and we have one more over here. We have the wedged bromine going to a dash, and a dashed chlorine going to a wedge. So then both of these are exactly the opposite of each other. Nothing stayed the same. Nothing retained its orientation. So since they both changed, we know this is going to be an enantiomer. And the last one, we have this one comparing with this one. Bromine on a dash, bromine on a dash, stayed the same. Chlorine on a dash, chlorine on a wedge. They both changed. So one's the same and one's different. So we know that's what we said what a diastereomer was. So that's a diastereomer. Okay. Just a quick little review from last week's session, the week prior to the 2nd of October. We went over how to prioritize groups on chiral carbons, and again, so you can have a good understanding for what chiral carbons are, we went over that in that video, so definitely watch it. But a quick little review regarding that. We first have to see if we have any chiral carbons here. So as you can see, this carbon right here would be considered chiral, and chiral carbons are labeled with a star. And the reason it's chiral is because there's 4 different groups coming off of it, and they're all different. So the first thing we're going to do is prioritize these different groups coming off the carbon so that we know which way the configuration for it will be. So we know that this one will be 1, this one will be 2, this one will be 3, and then there's an understood hydrogen in the back, so I'm not even going to worry about that. It's an understood dash, right? So what we're going to do is we're going to make a circle going from 1 to 2 to 3, just like that, okay? And yeah, so once we see it going in one direction, we're going to determine what that direction is. Give me 1 second. Right, so we see that this is going this way, right? So we're going that way. We're turning towards the right. So if you're turning towards the right, that's an indication for this to be an R configuration. And also we went over how if this bromine were to have been on a dash as opposed to have being on a wedge, that would have made the hydrogen on the wedge. And if you have your 4th priority group on that wedge, you have to flip the orientation. But since we have this 4th orientation, which is a hydrogen on the dash, we don't have to flip it. Okay? So one thing to note is that we talked about R and S the week before. So there's one concept called Racemic Mixtures. We'll talk more about this later, and you will also speak about it in lab, but just it's a good thing to factor in the back of your mind. It's when half of the molecules want to rotate one way and the other half want to rotate the other way. So there's like a split between the R and S configurations and what they want to be. So just remember that, but that's all you need to know about it for right now, okay? Okay. So next concept is called Meso Compounds, okay? So there's 4 things that you want to remember when it comes to Meso Compounds, okay? The first one is that there has to be an internal plane of symmetry. That's what POS stands for. The second is that the structure as a whole has to be achiral, okay? The next thing is that it has to be superimposable. And the last thing is that the structure itself has to have chiral carbons within the structure. Like there has to be chiral carbons, right? So for a meso compound to be considered meso, you have to have 2 chiral carbons in there, meaning 2 carbons with 4 different groups coming off of them. But at the same time, for something to be considered meso, those 2 chiral carbons that are present in turn make the whole structure achiral. Okay? So if you look at this one, we drew 2 structures side by side, and these aren't enantiomers or diastereomers of each other. They are absolutely identical, as you can see. And just so you can kind of visualize what a meso compound looks like, we have that internal mirror plane of symmetry going down the middle, proving that both sides are exactly the same. And we also have those two chiral carbons going through the structure in both sides. So we have that internal mirror plane of symmetry, that's a check. We have two chiral carbons or two chiral centers, same thing, that's another check. We have superimposable images, meaning it's like this way, like here's my hand. My hand is superimposable when I turn it to the other side, and it's exactly the same this way. So that's exactly what's here, right? We have the structure here, and it's superimposable to itself like that. So all four are checked. Same for that, they're just identical structures, okay? And then the same thing here. We have another structure with that internal mirror plane of symmetry going down the middle. This is identical to this one. We have those four checks to go through. Does it have the internal mirror plane of symmetry? Yes, it has it, because both are the same on either side. Are they superimposable? So we have the image here, and then we're going to flip it over like that. So yes, it's also superimposable. Are there chiral centers in the structure? Yes, because if we look at this one, this carbon's bonded to this group, then a hydrogen, and then a methyl, and then there's another one going to a carbon. So this carbon has four different groups coming off of it, and the same thing can be said for this. Okay, so a good thing to write down with your notes also with everything else is this. All meso compounds are achiral compounds, okay? That contains stereogenic atoms. Stereogenic meaning the stereo center or the stereo chemistry. Now, having said that all meso compounds are achiral, that does not mean that all achiral compounds are meso. There can be situations where you don't have a meso compound even though it's achiral, and we'll go over those examples right now. Okay, so just to explain that, we have this structure here, and then we have the same structure shown stereochemically with these 3D orientations. So as you can see, I pretty much drew every version of it with the bonds and with the dashes and the wedges, but there's one that I left out, and that's the one with like this, both having been on dashes. We'll explain why I'm not showing that, okay? But so one second. Okay. So once we prioritize these, we see that this group would be an R. I'm just going to do the first one. I'm not going to do the rest. Okay, so we make it, and it's going to the right. So we have the R. Same thing for here. We'd also have an R. Now, before, like once you see this structure, before you label them or prioritize them, a quick way to know what the orientation would be is if you have this group and it's flipped on this group into a wedge, I mean a dash, that means its orientation is automatically just going to change from what it is. So you don't have to prioritize them necessarily again. I mean, if you do, you wouldn't be wrong, but it would just take less time to know that if I prioritize this and it flipped, then it's automatically an S. Vice versa for this one as well. So again, a good practice of what we learned. How do these two compare? These two are going to be enantiomers because both changed 100%. This changed to a dash, and this dash changed to a wedge. Now, the third stereoisomer of this group, okay? If we were to have both bromines on that wedge, right? The question I'm asking you guys is, would it be meso? And if we go through the checklist, we can see that it will be because we have that internal plane of symmetry. They're both pointing out. Both the bromines are pointing out of the group, right? Now the next question, so we have that check. The next question, does it have chiral centers? So is this carbon that's bonded to this bromine, this methyl, and then this group with the hydrogen, are they all four different groups? And when you ask yourself, you'll say yes, because they are all four different. Is this one the same? Yes. The same can be asked for this, and you can realize there's 4 different bonds coming off of this carbon. So we have those chiral centers, we have the internal plane of symmetry, and knowing that, we know the whole structure in itself will be referred to as an achiral structure. But the reason it's also meso is because of the fact it has that internal plane of symmetry, meaning you have this and it's the same on the other side. Okay? Next. Okay, so a good example to kind of just get a good understanding for meso is how many planes of symmetry are in this cyclohexane, right? There's a lot, clearly, right? So you can have one going like this, you can have one going like this, you can have one going like this, you can have one going like this. Like, they just never end, right? So if you have one internal plane of symmetry, that's a good hint for the compound being meso. But what did we say? We said that you also have to have chiral centers, right? So as you can see, this carbon over here is bonded to 2 hydrogens which aren't drawn, right? And then having said that, that carbon is also bonded to 2 more carbons which are both bonded to 2 more hydrogens. So the fact that there aren't any chiral centers in this structure mean that it is not meso. It has those planes of symmetry in it, but it's not a meso compound because of the lack of the chiral centers. Chiral centers meaning 4 different groups bonded around it. Okay, so let's take this further and compare these structures that we have drawn over here. So this structure right here is this one meso. As you can see, this carbon is bonded to 1 bromine, but it's bonded to 2 carbons that are the same here. So it doesn't have any chiral centers, okay? And it doesn't necessarily have a plane of symmetry either. So we know that this one would not be meso, okay? Over here, this question we can see and ask ourselves, does this have an internal mirror plane of symmetry? Well, if we draw that line going through the middle here, it seems to be that this one does have a mirror plane of symmetry. Okay, that's good, but we have some more checkoffs to see, okay? Does this carbon seem to be a chiral carbon? Well, we have one carbon that's bonded to this bromine, then this carbon that's bonded to this carbon, and then this carbon that's also bonded to this carbon. Now, your initial instinct would be that, okay, these are both CH2s, so they're both the same. So this can't be chiral, but you'd be wrong because you don't just look off of that spot directly coming off this side and this side. You go to the first point of difference. The reason we didn't go any further on this is because if you look, they're all CH2s with nothing bonded around it. But over here, if you go further from this one here, you're at a CH2. When you go from this one further, you don't have that CH2. You have this bromine. So the fact that when you get off of this one has a CH2, this one has a CH2. You're supposed to go further. Over here, before you get to the bromine, you have another CH2. But over here, you get directly to a bromine. So, having said that, there are different carbons. So then this group is chiral. Same thing for this one. So we have 2 chiral compounds in the structure. We have that internal mirror plane of symmetry. So this is a meso compound. And since it's a meso compound, overall, the entire structure is achiral. Okay. Now with this one, okay, we have we're going to see if this one's meso now. So for meso, we want to see if there's an internal mirror plane of symmetry. We do have that here. We have that internal mirror plane of symmetry. But now we have to see if they're chiral carbons. Over here, we have the carbon bonded to CH2s. Okay, let's see if we have anything different. Two CH2s again, they both go to a bromine, so they don't have chiral carbons. And to be meso, you have to have those. So is this structure meso? No, it's not, because it doesn't have those two elements that this one does that we just spoke of. Okay, I'm going to continue on. So, just like we did with this, we drew out the stereoisomers of it, right? But there's a good checking system for that to see if you drew the right amount of stereoisomers. And that's with this. The formula is 2 to the n. 2 stands for the number of chiral carbons. And n stands for the number of possible stereoisomers. Okay? So if you look at this structure, how many chiral carbons are in this structure? I'll give y'all like 10 seconds. So when I asked this question on the 2nd of October on Monday, everybody was mostly saying 3 because they saw 3 structures coming off of it with different orientations. But just to review, we got to know that chiral compounds mean that the carbons have 4 different groups coming off of them. So when we look at this one, we have this carbon bonded to a bromine, bonded to a methyl, bonded to a carbon with a chlorine, and then a hydrogen in the back. So these 4 are all different. So this one's chiral. Okay? And this chlorine here is bonded to a carbon, which is bonded to a bromine. Then there's a hydrogen pointing out of the paper. And then there's another carbon that's bonded to a carbon, that's bonded to a carbon, that's bonded to a carbon. So that's different from this side, right? So this too is also a chiral group, a chiral carbon. But if you look over here, this carbon here is bonded to a methyl, then another methyl, then a hydrogen, and then these carbon groups coming off. The fact that this is identical to this does not make this a chiral carbon. When I say chiral carbon, I'm talking about this. Okay? So a way to know how many stereoisomers there's going to be is we take the number of chiral carbons, which we have, we take the number of chiral carbons which we have, which is 2, and then the number of stereocenters two's a constant. 2 is always there. So the number of stereoisomers that we have, or the stereocenters. So sorry, this is actually supposed to say stereocenter, which is synonymous with chiral carbon. This equation is going to give us the total number of stereoisomers. Okay, so we had 2 chiral carbons, so we have 2 squared, which is 4. So we're going to have 4 possible stereoisomers with these. Okay, so that's just a quick little formula to double check how many you're drawing. And just to go over this one again, as you can see, there's 2 chiral carbons here, so it would be 2 squared as well. But if we were to have drawn that 4th one, it would have been a repeat structure, which is identical to this. So that's why we only drew 3. So when you do this formula, the answer is going to give you 4 total possible ones. So you're going to have to see how that 4th one is compared to all the other 3 to make sure you're not drawing the same one again. Okay? Okay, so we spoke about Fischer projections briefly the week prior to the 2nd of October, but we're going to go into a little bit more detail regarding them and kind of grasp this concept as much as we can, okay? Alright. Okay, so when you're drawing a Fischer projection, it's just another way of looking at the same structure that you have, right? Okay, so before we do that, just another example, I guess. We have the chlorine and the bromine. These are both chiral centers, 2n, 2 squared, so we're going to have 4 total isomers for this question too. Okay? Actually, I'm going to go over I think we have another example. Yeah, this one is a better example because it's going to incorporate three different things in this one. So let's do this one. Okay. So first thing that we're going to do is what our goal is, we're going to try to convert this line angle structure into a Fischer projection. But before we do that, we're going to prioritize all of the groups in this structure, right? So we're going to look at this one. So we have the priority that we do regarding molecular weight to see which one goes first. Bromine is going to be the first priority. We have this carbon bonded to another carbon, and then this carbon bonded to another carbon, but it follows into a bonding of more carbons and then a bromine. So this one's going to be 2, this one's going to be 3, and 4 is behind the paper, so that's going to be on the dash. So we know that we're not going to have to flip this orientation. So once we draw the circle, we see that our steering wheel is going to the right, so meaning that this is going to be in R configuration. Okay, so we're going to look and see where our other chiral carbon is, and that seems to be right here. We have this carbon bonded to a bromine, and then this carbon is bonded to a methyl, and then this carbon is bonded to the carbons with the bromine at the end of it. So we know that it's also chiral, so that's good. We have this one to be 1, this one's 2, and then this one's 3, and then the hydrogen's pointing out of the paper, pointing in the paper. So we know that we won't have to flip the orientation for this one either, because the 4th priority is on the dash. So once we draw this, we see that the steering wheel is again going to the right. So this is going to be an R configuration as well. Okay, so what we're going to do is draw it on this structure just as it is. Okay, so what we're going to do is this carbon is bonded to another carbon. Okay, so we have that carbon, which is a CH3, right? This CH3 is bonded to this carbon. This CH3 is bonded to this carbon. Okay, so I'm just trying to help you guys see how this is happening. All right. Having seen that, we see that that carbon is bonded to a bromine as well as a hydrogen. So we're going to have to put the hydrogen and the bromine on either sides of these. But we're going to test and see if we draw it correctly. Okay? So I'm going to draw the hydrogen over here. And I'm going to draw the bromine over here. We'll double check and see if we drew it right, but for now, just go ahead and draw it, okay? And then this carbon corresponds to this carbon, and it has 2 H's on it. So it doesn't matter which side you put these H's on it because they're identical. Then this carbon corresponds to this carbon. And again, we have to see if we draw the bromine and the hydrogen on the right spot. So I'll just draw the bromine and hydrogen here and check if we drew it right in a second. And then that carbon's bonded to another group, which is that CH3. Okay, so what we're going to do is we know that these orientations have to be R. So the way you see if you drew it correctly on your Fischer projection is you're just going to prioritize them like normal, just like we've been doing, okay? So we have this. So this chiral carbon corresponds to this chiral carbon, and this chiral carbon corresponds to this chiral carbon. So we're going to see if the prioritization of it is going to yield us to go into the same answer as this one. So this carbon is bonded to this bromine, so this prioritizes as 1. This carbon is bonded to this carbon, which is bonded to more carbons as opposed to just being bonded to one carbon there. So this one will be 2, and then this one will be 3. And when we draw it, we see that it seems to be going to the right. But if you refer to the last video, which we did prior to the October 2nd review, is I explained how everything on a horizontal line on the Fischer projection is a wedge. It's like a bow tie. Remember a bow tie and you'll never get it wrong. And then everything going vertically up and down is on a dash. Okay? So two horizontal lines. This is how a Fischer projection is laid out. Everything horizontally is a wedge, and everything vertical is a dash, because you're looking at this from a different angle, okay? So having said that, our hydrogen here would be on that wedge, which is what this explains. So if our orientation here is showing to be R, but the fourth priority is on that wedge, we have to flip it. So since it's an R, we're going to flip it to an S. So it looks to be R, but we're going to flip it because the fourth priority group, which is the hydrogen here, is on the wedge. Okay? Here we're not doing anything because it's not chiral. Same thing for here. So we're going to prioritize everything. We have 1. Then we have 2 up here because there's a higher priority up there. And then 3. So once we draw this, we seem to be going to the left, right? So we seem to be going to the left, but again, just like the prior one, we have the hydrogen on a fourth priority, which is on that wedge. If it's on the wedge, you always have to flip it. So if this seems to be R, it's actually, if this seems to be S, it's actually going to be R, okay? So now what we do is we compare how the conformations are to this structure. Over here, we have the R, but over here, it's shown as S. Over here we have the R, and over here we have R. So we drew this one correctly, but we're going to have to flip this one to make it identical to this. So the final answer for this, you draw it. Again, these are the same. These are the same. This we leave the same too as this because we had the correct configuration with it after we drew the circle. But Okay, same for this one as well. We didn't do anything to this. But this top one, we saw that we had the S configuration after having drawn it, but we need R. All you do is flip the horizontal ones to get that, okay? BR on the left and H on the right. So that's how you do this one, okay? Okay, we're just going to incorporate what we just learned with isomerism again, okay? So I have these 3 drawn out, and I just want y'all to see and try to know what they are compared to each other. Like, how does this compare to that? How does this compare to this? And how does this compare to this? So I'll give y'all like 20 seconds to see if they're diastereomers of each other or if they're enantiomers of each other, and we'll go over it. Okay, so we have these Fischer projections, and we're just going to see how they compare. If you look at this one right over here, the one on the left, you see that the ethyl group is on top, methyl's on bottom, this OH on the left, and then the OH on the right. So what we're going to do is we're going to compare it. Over here, the top and bottoms are exactly the same. Also, those are the ones that are the same, but if you look at this, the H, which is on the left here, is now on the right, and the OH, which is on the right here, is on the left. Same thing for the bottom, they flipped on this one. So if you have that happening, pretty much what happened is this is flipped this way. What does that mean? Both of them changed, right? So they're those mirror images of each other. So these are enantiomers, okay? Now, we're going to compare this one and this one. We have the ethyl on top, methyl on bottom. The top stayed the same. It retained its positioning, but the bottom changed this time. The OH is on the right, OH is on the left. One stayed, one changed. That is known as the diastereomer. One mirror, one non-mirror. Same thing with this now. We're going to compare it. This HOH, OHH, they changed. HOH, HOH, this stayed the same. One mirror, one non-mirror. Again, that's a diastereomer. So pretty much we talked about everything that we went over on the 2nd of October, but I just did it again. If you guys have any questions about anything, go ahead and just put them in the comments and I'll try to answer them as much as I can. If not, if I'm not able to understand what you're saying in the comments or something, we can go over this next Monday before we start the rest of chapter 6 that we're going to incorporate with everything. So that's it, guys. Actually, before I finish, y'all definitely want to make sure to do as much practice as you can, please. Go to Zaid Faraj, go to Zaid Faraj's website, look at your notes in class, look at your worksheets, look at everything you get in workshop if you're in it, and try to do as much as you can so that once chapter 6 rolls around, you guys can do the same for that, because chapter 6 is a doozy. There's a lot of new things that you're going to learn. There's going to be a lot of reactions that we're going to incorporate, which is probably the bulk of what organic chemistry is. So it's a good idea to start doing the worksheets now so that once chapter 6 begins, y'all can definitely be on top for everything. Alright guys, good luck.